And we're back. I'm doing problem number 63 as a tutorial problem today. Let's get right into it. A farmer uses a tractor to pull a 150 kilogram bale of hay up a 15-degree incline. He's dragging it to the barn at a steady 5 kilometers per hour. The coefficient of kinetic friction between the bale and the ramp is 0.45. So part A, what is the initial kinetic energy of the hay bale? Just a by the by, before we get too deep into this, I had to re-upload this problem as of Wednesday morning. There was a small error in it regarding parts E through G, I think. So just a heads up on that. If you tried to attack this problem earlier in the week, look at the new file. It has changed a little bit. I'm working with the new file for this little video. So what's the initial kinetic energy of a hay bale? Well, we're always considering kinetic energy to be 1/2 mv squared, right? This is just something that we're kind of developing in the pit of our stomach, in our gut, in our core. Kinetic energy equals 1/2 mv squared. Now this problem is a little unique. There's no true initial, no true final. So instead we're just saying initially, when we first look at this point, maybe let's say a 10-meter segment up this ramp, initially the kinetic energy, right, we can find that if we knew the velocity of this hay bale. Velocity is 5 kilometers per hour, so 5,000 meters per hour. Let's turn that into seconds though. So I gotta have hours up here, and let's do minutes down here first. So how many hours, minutes? So 60 minutes in 1 hour. And I'm gonna do the same thing, minutes, seconds, 60 seconds in 1 minute, hours, hours, minutes, minutes. 5,000 divided by 60 gives me a velocity of 1.39 meters per second. So now I can calculate my kinetic energy. My KE equals 1/2 150 kilograms times 1.39 meters per second squared. If I were to calculate that, 0.5 times 150 times 1.39 squared, I get I get 144.9. You know what? Let's just say 145. 145 joules of kinetic energy to begin with. What's the final kinetic energy? Like I said, there's no true initial and final position right now. So this is a little bit more general here. We're saying that I'm going at a constant, a steady 5 kilometers per hour. So the final kinetic energy equals the initial kinetic energy. That's what we're trying to show here, which equals 145 joules. What does this tell us about the net work done by the environment? Well, if we write out our work kinetic energy theorem, we're saying that the external work from the environment is equal to the change in kinetic energy. If the change in kinetic energy is 0, based on what we just said, then the external work done by the environment also needs to be 0. All our forces do the exact same amount of work. It's not to say that the forces are all equal, but all their works when you sum them up, and all the forces when we sum them up, I suppose you could say they are equal. So draw a free body diagram of the bale of hay. What's the normal force on the bale? So this is bridging the gap from chapter 6, 7, 8. Let's draw a free body diagram. The easy force to draw is always my gravitational force. We're in an x prime, y prime plane. So I'm going to have the tension from my tractor pull up the incline. I'm going to have my gravitational force. Sorry, my frictional force. We already talked about the gravity force. The frictional force down the ramp. I have my normal force perpendicular to the incline. And then because we're on this x prime, y prime, of course I need to consider the FG y prime and the FG x prime components. We remember that this angle is 15 degrees. It's whatever the angle of the incline is. So we got to sum up our forces in the y prime direction. In the y prime direction we have two forces. We have the normal force, and then we have the y component, the y prime component of the gravitational force. And it's worth asking ourselves, does this bale of hay accelerate off the ramp or into the ramp? And I would say no for both of those. So the net acceleration is going to be 0, which allows me to say that the normal force is equal to the y prime component. The y prime component of gravity, right, is our adjacent side to this angle. So I'm going to use cosine. I'm going to say mg cosine of 15 degrees. And if I calculate that, 150 times 9.8 times cosine of 15 degrees, I get 1400, and let's round it to 20 newtons. That's my normal force on the bale of hay. How much work is done by the normal force on the hay bale system? And we want to explain that. So if we're thinking about work, right, work is F dot our displacement. We can write that another way. We can say F, the magnitude of F times the magnitude of our displacement times cosine of our angle between them. So if we think about this, I am displacing up my slope, my incline, and then my normal force is normal to the incline, right? It's at a perpendicular angle here, which means that for this cosine theta, what we're really saying is cosine of 90 degrees. Cosine of 90 degrees is 0. And so the work done by the normal force, let's just write an N there, is 0. Why? Because the normal force is perpendicular to displacement. This is a no work scenario. We need our forces to be at least partially in the direction of our displacement to do any non-zero work. Alright, so moving right along to part E, how much work is done by the gravitational force on the hay bale system over a 10-meter segment of the incline. So we're giving ourselves a displacement of 10 meters here. I actually want to go back. I want to copy this free body diagram that we drew. And I want to copy it because I think it's kind of an important reminder to us as to what's all going on here. And let's shrink it just a little bit, give ourselves more real estate. So if we're thinking about this, how much work is done by the gravitational force? So I know that I'm displacing, right, in this direction, but I have this gravitational force just straight down. So, I could do this one of two ways. I could just do straight up work definition, right? I could say that the force times delta x, put these magnitudes in here, times cosine of the angle between them, that would be mg times delta x times cosine of, well, what is this angle? That angle is 90 degrees plus 15 degrees, so a total of 105 degrees. If I calculate that, I have 150 kilograms times 9.8 meters per second squared times 10 meters times cosine of 105 degrees. I'm left with cosine 105. Make sure that you're in degree mode and not radian mode. I get negative. I said 105 instead of 150. There we go. That's better. Negative 3,800, and I'm going to round this to 5 joules. That's how much work gravity does. Now, another way of interpreting this dot product is saying what is parallel. What's in the parallel direction to the displacement? Well, the FGX is the parallel component of the gravity force in the direction of delta x. If we thought about that, if said x prime component, right, I could say FGX prime is mg sine 15 degrees. Delta x is still 10 meters. And then the cosine theta would be cosine of not 90, but 180 degrees. That would give us a negative 1. So the work done by gravity in this case would be 150 kilograms times 9.8 meters per second squared times sine of 15 degrees times 10 meters times cosine of 180 degrees. And when you plug all of that into your calculator, sine 15, cosine 180, which we know is just going to give us a negative, we get negative 3,804.6, which we're going to round to 5 again. Get the exact same number. The exact same number. So it doesn't matter how we want to go about this, we get the same number, which is really convenient. I think this way of just saying what is the net force, what's the total force, what's the total angle between these two vectors, plug and chug, I think that's a little bit simpler than trying to actually figure out the parallel component before calculating. So how much work is done by the frictional force on the hay bale over this 10-meter segment? So for the frictional force, right, we need to say Ff is equal to Fn times mu k. We actually have a number for Fn. Did that back on the other page. We said that that was 1420 newtons. So 1420 newtons times mu k, which we said was 0.45. 1420, 0.45. I get 639 newtons. Now this, if we go back over to our free body diagram, this is 180 degrees opposed to delta x, so it's just pointing in the opposite direction. I can say the work done by friction is going to be the frictional force times my delta x, which we know is 10 meters times cosine of 180 degrees. I'm going to have 639 newtons times 10 meters times negative 1. and I get 6,390 joules. And it's negative. Sorry, I forgot the negative. Alrighty. So that was part F. How much work is done by the tension force on the hay bale system? So this is the tension that the tractor is pulling the hay bale with over this 10-meter segment of the incline. I could figure out what tension is and then do the exact same thing, but I think there's a quicker way of doing this. When we go back to our first part here, first two parts, right? What we've said is that we're not changing the kinetic energy of the system at all, no matter where we are on this slope. We have the same kinetic energy. We have the same velocity. And so what I've said is that the total external work by the environment is equal to 0. Flash forward over here, I need to have the work done by tension plus the work done by friction plus the work done by gravity to all equal 0 when I add them up. So the work done by tension should be negative the work done by friction plus the work done by gravity. It's negative because all of this stuff is negative, the friction and the work, the gravity work. So let's actually do that. I have negative 6,390 joules plus negative 3,805 joules. I get a total work done by tension. Let's do that. Of 10,195 joules. It's positive because it's in the same direction as displacement, and it completely balances out the work done by the other forces. So finally, using an expression used in the lecture about power, which was lecture 9, what's the tractor's power output? This is tricky. Normally we say power is equal to dE dt. We don't have a time period to actually talk about this, right? We could also say delta E over delta T. There's no time interval. There was a different way of talking about it that we came up with. Power was also equal to F dotted with our velocity. So if I think about this, I have a velocity upward here of 1.39 meters per second. And then I need to know what is the force that I'm pulling on this thing with, right? What is the force that I'm pulling on this thing with? What is the tension force? And again, I could go back through and actually solve it using my free body diagram. I don't recommend that. We have the work done by tension. The work done by tension is going to be equal to the force done by tension, right? Let's just write that as T times delta X. And since they're parallel to each other, this is actually true. So there's no cosine here because the cosine of 0 is 1. So if I want to actually find tension, right, what I can say is that tension is equal to the work done by tension over the displacement. So 10,195 joules over 10 meters should give me the tension force of 1,019. Let's just round it to 20. 1,020 newtons. I think that's going to be easier. So that's my tension force. It's in the same direction as my velocity, so the power, 1020 times, so this is newtons times 1.39 meters per second. I get 14 1,417.8, not joules, joules per second, or another way of saying that is watts. So that is the power output from the tractor to go at a steady rate. That's number 63 from chapter 9. Sorry this one was a little bit longer, but if you have any questions, let me know.